Hello viewers, welcome to add-on. In this question, we are asked to describe the construction, operation, and VI characteristics of a PN diode and what do you mean by cut-in voltage. So let us start by PN junction diode. So what is a PN junction? This is the question that arises first. So we all know about semiconductor, right? So semiconductor are what? Semiconductor materials whose conductivity lies between the conductors and the insulators. Okay. And this semiconductor are specifically of two types: intrinsic semiconductor and extrinsic semiconductor. Okay. And this extrinsic semiconductor can be further classified into P-type semiconductor and N-type semiconductor. And this classification are based upon the doping. Okay. In the P-type semiconductor and in the N-type semiconductor, we use different level of doping because in the P-type semiconductor, there is abundance of holes. In the N-type semiconductor, there is abundance of electrons because in the N-type semiconductors, we use in the N-type semiconductor, the type of dope which is used is a pentavalent atoms. Okay, so in the P-type semiconductor, we use pentavalent atoms which has a valency of 5, and in the N-type semiconductor, we use atoms which have a valency of 3. These are trivalent atoms, these are pentavalent atoms, and we can also say that this pentavalent atom is doped within the impurity, and this trivalent atom are doped within the impurity. Okay. So what happens if the impurity they consist of 4 electrons, then these 3 electrons will combine with the 3 electrons of this impurity, and 1 electron will be left out. So there will be abundance of electrons, but what happens here is the 4 electron of the impurity will combine with the 4 atoms of the pentavalent impurity. So one will be left out, or one will not combine with anything. So there will be abundance of holes. Okay. So now our discussion will be between P-type and N-type semiconductor in a PN junction. So PN junction is an interface or a boundary which is formed between two semiconductor material, namely PN junction or P-type or N-type semiconductor. So PN junction, this is a boundary or an interface, okay, which is formed between two semiconductor, namely P-type semiconductor and N-type semiconductor. So this is the boundary, okay. This is the boundary or the junction which is present between the P terminal and the N terminal, and this junction is known as the PN junction. Okay. So uh, let us discuss about the construction or working of this PN junction. Okay. So in the N-type semiconductor, as I have said, there will be abundance of electrons, and the electrons I am denoting here by negative sign, or we can also represent it by dot. It will be better to understand. These are all free electrons, and in the p-type material there will be holes. Okay, these are all empty holes, and beneath this junction there is a depletion region. There is a depletion region which maintains the electrons in the n-type semiconductor and the holes in the p-type semiconductor. It cannot allow to pass the holes from the p side to the n side, or to pass the electrons from the n side to the p side. This is the main function of this depletion region. Okay. So if we use a different semiconductor material to make a PN junction, there is a boundary that would inhibit the movement of the electrons from one side to other side by scattering process. But we won't be considering that. We will be considering a silicon type semiconductor material. Okay, we will be only considering a silicon type semiconductor material. Okay. So the biasing condition of this PN junction is mainly of 3 types. One is zero bias, one is forward bias, and one is reverse bias. Okay. So during zero bias, no external voltage is applied. During forward bias, the positive terminal of battery is connected to the P side and the negative terminal of the battery is connected to the N side. And during reverse bias, the condition just interchange. The positive terminal is connected to the N side and the negative terminal is connected to the P side. Okay. So before understand the biasing, we will get to look at how the scenario works inside. Okay. So let us start by understanding the diffusion and drift process. Okay. So these diffusion and drift process are the main two driving factors in a PN junction. Okay. Because there is a difference in the concentration of holes and the electrons on the two sides of the junction. In the N side, there is little or no concentration of holes, and in the P side, there is no concentration or little concentration of electrons. So what happens? The holes on the P side will try to diffuse to the N side, and the electrons from the N side will try to diffuse to the P side. Okay. So this gives rise to a diffusion current across the junction, which gives rise to a diffusion current across this junction. Okay. So when an electron diffuses from the N side to the P side, an isolated donor is left behind on the N side. Okay, which is immobile. So as this process goes on, a large amount of positive charge is accumulated on the N side of the junction. Similarly, as the holes grow from the P side to the N side, acceptor atom is left behind on the P side. Okay. So this also result in a formation of a large layer of negative charge in the P side of the junction. This region of the positive charge and the negative charge on the either side of the junction give rise to the depletion region, which I have denoted by this kind of box. Okay. So what happens when we are applying zero bias? Now we will understand biasing. So first, zero bias. So during zero bias, there will be no movement of electrons from the inside to P side or no movement of holes from the P side to the N side. Now during forward bias, if we apply the positive terminal to the P side and the negative terminal to the N side. Okay. So when the P type is connected to the positive terminal of the battery, the diode will be forward bias because the built-in electric field at the PN junction, which is in this direction, the built-in electric field is in this direction, and the applied electric field is in this direction. So the built-in electric field and the applied electric field are in the opposite direction. So when both the electric field add up, the resultant electric field has a magnitude which is lesser than the built-in electric field. This results in a less resistive and a thinner depletion region. So this depletion region, suppose this region is like this. So the box now will become like this small type. So the depletion region will decreases. Okay. And the depletion region resistance become negligible when the applied voltage is large. In the silicon, at a voltage of 0.6 volt, the resistance of the depletion region becomes negligible. So if we apply a 0.6 volt biasing, externally, the resistance become negligible. Okay. So if we draw the curve, it will be like this. So for small values of voltage, the current will increase slowly, and after attaining a particular value, which is 0.6 volt, it will increases gradually. So this value of voltage or this point after which the value of current is increasing sharply, this point is known as the cut-in voltage. Okay, this is known as the cut-in voltage. This is 0.6 for case of silicon and 0.3 in case of germanium. And now the reverse bias. So when the P type is connected to the negative terminal and N type is connected to the positive terminal, the PN junction is reverse biased. So in this case, the built-in electric field and the applied electric field are in the same direction. And when these two fields add up, the resultant electric field will be we can say will be in the same direction in as the built-in electric field, and it will create a thicker depletion region. So here the depletion region at zero bias was like this. Then after applying forward bias, it becomes like this. Then after applying reverse bias, it becomes like this. Okay. So the depletion region become more and more thick. And if the depletion region becomes more and more thick, it becomes more resistive and thicker if the applied voltage becomes larger. Okay. So for increasing the voltage, the current will increase. This is the forward bias. When we are increasing the value of voltage in the forward direction or in the positive direction. But if we decrease the value of voltage in the negative direction, the current will saturate. Okay, so this is the VI characteristic. And one question may arise that why we are getting a sudden spike of current at this particular point? Because we can see during the reverse bias, up to a few voltage of value, suppose up to minus 5 volt, the value was almost constant or negligible. But after attaining minus 5 volt, the value suddenly increases, the value of current. So this is the current value and along the y-axis, and this is the voltage value along the x-axis. So after attaining minus 5 volt value, the current suddenly generates a spike and it is increasing gradually. So this happens because each and every single PN junction, they function as a Zener diode, and is Zener diode as a breakdown voltage. And this particularly occurs when the PN junction is operating in a reverse bias condition. Okay. So during the reverse bias condition, the PN junction acts as a Zener diode. And this 5 volt, this is the breakdown voltage. I am representing here as BV. And if the PN junction attains this breakdown voltage, if we further decrease the value of voltage like minus 6 volt, minus 7 volt, then the current will increases exponentially. And after that point, the current will become so large within the PN junction that the PN junction will burn out or it will become infunctional. Okay. So this is all about the PN junction. Thank you.